Okay, hey folks, let's go ahead and explore the properties of these spherical harmonics. So this will be a pretty short video, and as you can see here, I've got Mathematica in front of me. Of course, Mathematica has the spherical harmonics built in. So let's go ahead and take a look. So what we ended up with last time, we solved, or we made our best attempt to solve the particle on a sphere problem. When we did that, the normalized wave function for that, so n psi, we call a new function here, this YLML, that we refer to as the spherical harmonics. In the derivation of the solution, which we skipped over, a new quantum number appears. So this L comes from solving the theta component of the spherical harmonic. So we get this new quantum number called L, which we refer to the angular quantum number, and that can take on values 0, 1, and 2. What we also didn't get to, because the math is just a little bit complicated, when we solve the energy solution of the spherical harmonic, we get the following. It goes as L times quantity L plus 1 times h bar squared over 2 times I, where L can take on values 0, 1, 2, and 3. And what we also get out of this, our original quantum number that we came up with, ML, has dependencies on L. So ML can take on values L all the way through minus L, including integers and 0. Our degeneracy will go that there are 2 L plus 1 values of ML. So for example, if L is equal to 0, ML only has one value, and that value is 0. If L equals 1, we can see here 2 times 1 plus 1 gives me 3. So there will be 3 values of ML, and those values will be -1, 0, and +1. And just as one last example, if we have L is equal to 2, we know 2 times 2 plus 1 is 5. So that will be 5 values of ML, and they are -2, -1, 0, +1, and +2. So that may be familiar to you all from your general chemistry days. And these come from solving the particle on a sphere problem. So here I've got the spherical harmonics, the equations in front of me, and you can see they are rather complicated. So notice here at first when we have L is equal to 0 and M is L equal to 0, we just get this really simple looking function. It's just a constant, which is consistent with what we came up with in a particle on a ring. So now if we allow L to take on non-zero values, you can see we start to get dependencies on theta. And this is really cool. If you look at this, take a look at all the ML equals 0 values. And you'll notice here for all of the ML equals 0 values, there are no dependencies on phi. So that's rather interesting. We're going to come back to that in the coming videos. And so now when we notice on the non-zero values of ML, we start to see dependencies on phi. So for the plus minus 1, you can see we've got this e to the plus minus I phi. And we can see that that also appears now for our plus minus 1. Again, there's e to the plus minus I phi. For plus minus 2, we get e to the plus minus 2I phi. So what we're seeing there is that solution in phi, which you recall went e to the I ml phi. So we can see that part of the solution in the spherical harmonics right there, right? For ml is plus or minus 3, we've got e plus or minus 3I phi. So we can see it's not really that mysterious now where our solutions went. We've got the same solutions that we came up with before. We've just got this extra complication with our dependency on theta. So what do these all look like? Well, the book provides some graphs of what these solutions look like. We've got L down in the rows and ml in the columns. But of course, because Mathematica has these built in, we can take a more intuitive look at these. So the way that these are built in Mathematica, it goes spherical harmonic Y, and the placeholders go L, followed by ML, and then theta phi dependencies. So here you can see I've got to manipulate plot here. And to plot these, we've got to use the code spherical plot 3D. So that's going to give us a three-dimensional plot with theta and phi dimensions. Okay. So let's take a look at some of these. So you can see where we've got L is equal to 0 and ML is equal to 0. We just get a sphere, which makes good sense because if you recall, that equation was just a constant. And with the radius being constant, we end up with a sphere. So if we now go out to L is equal to 1, oops, let's see. And yes, L is equal to 1 and ML is equal to 0. There we get this rather kind of like, dumbbell looking shape. It maybe kind of looks like a p orbital to me. I don't know what you guys think. And now if I go over to the ML is 1, I get this like, donut looking shape that they predict over there. And of course, I could go back to the ML equals -1, and I get the same thing because the plus minus 1 solutions are degenerate. So we can go to the L is equal to 2. Let's do that. L is equal to 2 and ML is equal to 0. And I get this crazy thing that kind of looks like a d orbital. But we don't know that yet, right? And looking at the other ML solutions, we can see that we get those shapes as predicted in that spreadsheet over there, or in this figure. So now there's something cool that happens, though. If I try to break this quantum number dependency, which recall, right? ML takes on all values of negative L through positive L, every unit of 1 and including 0. So for example, if I have L is equal to 2, I can't have ML is equal to 3. And if I do that, if I try to break Mathematica, look, it doesn't give me a solution because that quantum number is not possible. Or the combination of these quantum numbers aren't possible. But now if I step up and go to L is equal to 3 and ML is equal to 3, I get a solution for that. So it's kind of crazy looking because I don't have the bounds like spread out for enough. But to test that out, right, if I go to ML is 4 and L is 3, we know that that possibility doesn't exist. So I don't get a solution for that. So this is pretty cool. And if you're thinking, man, these look like so close to the orbitals, I mean, kind of, but not really, then you've got a good eye. Because in the case of some of these, like if I go back to the L is equal to 0 and the L is 1 and ML is 0, I mean, this looks like a p orbital. And if you remember your quantum numbers, these are the correct quantum numbers to describe a p orbital. So we've got some deep connection here to the atomic orbitals as we learned them in general chemistry. So this means we're really close to having a solution to describe the full hydrogen atom. So very cool stuff. So we'll pursue this more in the coming weeks when we attempt to now allow the radius to no longer be constant, right? Remember, we did all of this under the assumption that the radius is constant. We know that's not the case. So we're going to have to further refine this model to include a non-constant radius. Okay, folks, I'll see you in the next video.